Welcome to Scientific Serenity. Tonight, we leave the familiar shores behind, traveling to the most remote and silent place on Earth, a place where water, ice, and time conspire to create a hidden force that flows through the very depths of our planet's oceans. This is not a story of what we see on the surface, but of what moves, unseen and profound, in the eternal darkness below. A story of a silent river, the Antarctic Bottom Water. To understand this river, we must first understand its source, Antarctica, not as a mere continent of ice, but as the beating heart of the world's coldest, densest, and most mysterious water. Our journey begins not with sophisticated machinery, but with the observations of those who first dared to venture into this white oblivion. Imagine the early 20th century, the heroic age of Antarctic exploration. Men like Robert Falcon Scott and Ernest Shackleton are not yet thinking of deep ocean currents. They are fighting for survival, for geographical glory, against the most brutal cold on the planet. But in their logs, in their meticulous records of temperature, ice formation, and wind, lie the first unconscious clues. Scott's final expedition, 1910 to 1913. Their ship, the Terra Nova, is locked in the pack ice. The men take regular soundings, measuring the depth of the sea with a weighted line. They note, almost in passing, that the water near the ocean floor is not just cold, but colder than the water above it. This defies simple intuition. Cold air sits above warm air. We expect the same in water. But here, in the polar extremes, the laws of physics play a different game. It is a tiny anomaly in a sea of data, a whisper in a blizzard. It goes largely unremarked upon, a curiosity for oceanographers back in London to perhaps one day ponder. The real clue, however, lies not in the water's temperature alone, but in its birth. Stand with me on the Ross Ice Shelf, a colossal floating plain of ice the size of France. The air is so cold it feels like a physical presence, a sharp, crystalline silence. Here seawater freezes, but when seawater freezes, it does so in a peculiar way. It expels its salt. The forming ice is relatively fresh, while the surrounding water becomes salter and therefore denser. This dense, icy brine sinks. It trickles down the shelf's edge like a slow, cold waterfall into the abyssal plains below. This process, known as brine rejection, is the first heartbeat of the great deep water formation. Now, shift your perspective from the ice shelf to the open ocean during the fierce Antarctic winter. The sea itself begins to freeze, creating new sea ice. Again, salt is expelled. The surface water becomes so cold and so saline that it can no longer stay aloft. It becomes heavier than the water beneath it, and so it begins to sink, not in a dramatic plunge, but in a slow, relentless descent, like grains of sand through syrup. This sinking is not a local event. It is a continental-scale process, happening along the fringes of Antarctica, where the ice meets the sea. It is the genesis of a mass of water so cold and dense that it will slide along the ocean floor for centuries, traveling thousands of miles. For decades, this sinking was theorized but not truly understood. Oceanography was in its infancy. The deep ocean was a black box. Ships could measure the surface. They could take samples from shallow depths, but the profound darkness below 2,000 meters was as unknown as the surface of the moon. The technology did not exist to track a body of water on its multimillennial journey. The deep sea was considered a static, lifeless, and largely irrelevant repository. Then came the pioneers who asked the right questions. In the 1920s and 30s, scientists like George Deacon began compiling data from various naval and research voyages. They started to see patterns. Charts of deep ocean temperatures showed persistent cold pools spreading north from Antarctica along the seafloor, like chilly fingers reaching into the Atlantic, Indian, and Pacific basins. These were not random. They were the footprints of our silent river. The breakthrough in understanding came from grappling with the simple yet profound concept density. In the world's oceans, water moves not primarily because of wind, but because of differences in density, a product of temperature and salinity. Warm, fresh water is light. Cold, salty water is heavy. The heaviest water on the planet forms in only two places, the Nordic seas near Greenland and the shelves of Antarctica. This dense water fills the ocean's deepest basins and begins a global pilgrimage. Our story's first true visionary of this hidden circulation was perhaps the American oceanographer Henry Stommel. In the 1950s, while many were focused on surface currents like the Gulf Stream, Stommel became fascinated by the abyss. He proposed a radical idea. The deep ocean is not stagnant, but is filled by these dense cataracts of polar water, which then slowly spread and rise across the globe in what he poetically termed the Great Ocean Conveyor Belt. It was a grand, unifying theory. Antarctica, in this view, was not the end of the Earth, but a mighty engine room, a pump for the planet's circulatory system. But a theory needs proof, and proof in the deep ocean requires more than a weighted line. It requires technology that could brave the crushing pressures and eternal night of the abyss. The stage was set for a new era of exploration, one that would move from the heroic age of geographical discovery to the heroic age of scientific revelation. The silent river was waiting to be heard. As we prepare to follow the first modern expeditions that would map this river's course, let your mind settle into the rhythm of this slow, cold world. Feel the immense weight of the Antarctic ice, a weight that presses down not just on the continent, but indirectly on the oceans themselves. Imagine the slow-motion cascade of dense water, beginning its journey in near-freezing darkness, destined to travel through the heart of the world's seas. Close your eyes for a moment and picture the scene at the edge of the ice. The stark, blinding white meeting the deep, endless blue. The only sound is the wind and the occasional groan of the ice. Beneath that blue, a process older than human civilization continues, unabated and unseen. It is a process of immense power and perfect silence. Let that silence be the canvas for our story. A story written not in words, but in temperature gradients, in salinity measurements, in the patient data points collected by generations of curious minds. We are about to dive into that data, into that cold, dark water, and trace the path of the planet's most important river that no eye has ever seen. But for now, simply breathe. Inhale the cool, clear idea of a world connected by hidden flows. Exhale the noise of the surface. We're going deep, deeper than any sunlight penetrates, into the realm where water, transformed by ice, begins its long, silent walk across the globe. The proof would come from ships, but not the wooden sailing vessels of Scott's era. It would come from steel-hulled research vessels purpose-built for the Southern Ocean's fury. Ships like the R/V Atlantis, the Eltonin, and later, the mighty Nathaniel B. Palmer. Their mission, to lower not just weights, but sophisticated instruments into the abyss, to listen to the ocean's whispers. The key instrument was the Nansen bottle, a simple yet revolutionary device invented in the 1910s. A metal cylinder lowered on a cable. It could be triggered at a specific depth to snap shut, capturing a water sample from that exact location. Along with it came reversing thermometers, which recorded temperature at depth. For the first time, scientists could build a vertical profile of the ocean, a column of data showing how temperature and salinity changed from the sunlit surface to the dark floor. Now, imagine yourself on the deck of such a ship in the 1950s. The air is biting. The ship rolls in the long, gray swells of the Southern Ocean. A team of oceanographers, bundled in thick parkas, is winching a rosette of Nansen bottles over the side. The cable whirs as it pays out, meter after meter, until hundreds, then thousands of meters have vanished into the dark, green water. They wait. The work is cold, monotonous, and physically demanding. But in each bottle retrieved, in each temperature reading, lies a piece of the puzzle. The data began to paint a stunning picture. Along the continental slope of Antarctica, particularly in the Weddell Sea and the Ross Sea, the profiles showed something remarkable. The coldest, saltiest water wasn't in the middle depths. It was at the very bottom, hugging the seafloor. This water was consistently around -0.5 to 0 degrees Celsius, 31 to 32 degrees Fahrenheit, barely above its freezing point and incredibly dense. This was the Antarctic Bottom Water, ABW, in the act of formation, caught like a photograph as it began its descent. But how did it move? To understand that, scientists needed to measure not just properties, but flow. Enter the swallow float, invented in the 1950s by John Swallow. This was a clever device. An aluminum tube weighted to be neutrally buoyant at a specific depth. Once launched, it would drift with the deep currents, emitting an acoustic ping. By tracking its position from a ship above, oceanographers could map the speed and direction of deep flows for the first time. When swallow floats were deployed in the North Atlantic, they revealed the southward creep of dense water formed near Greenland. The hunt was on for their Antarctic counterpart. The logistics were daunting. The Southern Ocean is the stormiest on Earth. Icebergs the size of cities drift through research areas. The cold is not just uncomfortable. It seizes machinery, ices cables, and tests human endurance to its limit. Yet the data trickled in, and it confirmed Stammel's grand vision. Deep, cold water was indeed flowing north from Antarctica. It moved not as a rapid river, but as a vast, sluggish sheet, perhaps only a few centimeters per second. But given the immense volume, thousands of cubic kilometers of water, this slow movement represented a colossal transfer of heat, salt, and dissolved gases around the planet. The 1960s and 70s saw the rise of international cooperative programs like the International Geophysical Year and later GEOSEC, Geochemical Ocean Section Study. These were the first attempts at a global census of the ocean. Ships from multiple nations crisscrossed the world's oceans, taking samples at standardized locations and depths. For the first time, the three-dimensional structure of the global ocean began to emerge from the data fog. The GEOSEC data was a treasure trove. By analyzing not just temperature and salinity, but also trace chemicals and isotopes like carbon-14 and tritium, left over from atmospheric nuclear tests, scientists could date the water. They could tell how long it had been since a parcel of water had been at the surface. The results were humbling. The oldest water, rich in nutrients and depleted of oxygen, was found in the deep North Pacific. This made sense. It was the end of the line for the conveyor belt. Water that sank in the Antarctic or North Atlantic had traveled for over 1,000 years before slowly upwelling in the Pacific. The Antarctic bottom water was now more than a theoretical curiosity. It was a documented, measurable component of the Earth's climate system. It was the foundation of the ocean's deep, overturning circulation. But a critical piece was still missing. The conveyor belt model suggested that this deep water must eventually rise to the surface to complete the loop. But where and how? The answer, once again, lay in the subtle interplay of density. As the Antarctic bottom water flows north along the seafloor, it is slowly warmed from above by the overlying, slightly less dense water. This warming, minuscule per century, is enough to gradually reduce its density. Simultaneously, it mixes with surrounding waters. This incredibly slow process, over centuries and across ocean basins, eventually allows the deep water to become light enough to upwell. This upwelling isn't a dramatic geyser. It's a diffuse, basin-wide ascent, lifting nutrients from the abyss back toward the sunlit surface, where phytoplankton can use them. In a very real sense, the silent river feeds the ocean's gardens. By the late 20th century, the narrative was solidifying. Antarctica's ice was the trigger. The brutal cold and the salt-rejecting formation of sea ice created a unique, super-dense water mass. This water sank, displacing the ancient deep water before it, and set in motion a planet-spanning circulation that took over a millennium to complete. This circulation moved not just water, but heat. It carried cold Antarctic chill into the deep tropics, and it helped transport warmth from the equator toward the poles. It was, and is, a central regulator of Earth's climate. But with understanding came new questions and a growing sense of vulnerability. This system, so vast and ancient, depends on a delicate balance. What happens if Antarctica warms? What if less sea ice forms? Or if glacial meltwater pours a layer of fresh, light water onto the ocean surface, capping off the formation of dense brine? Could the silent river slow down, or even stop? The implications were, and are, profound for the global climate. Our story now pauses at this threshold of modern understanding. We've moved from the chance observations of explorers to the systematic measurements of 20th century science. We've seen the silent river emerge from myth into mapped reality. But the story is not static. The river is changing. The next chapter of this tale involves satellites, autonomous robots, and a pressing urgency to understand how this ancient pulse of the planet will respond to the rapid changes we are now imposing upon it. But before we step into that modern drama, let the scale of what we've learned so far settle in your mind. A process that begins with the freezing of a single snowflake on the Antarctic plateau, or the formation of a tiny crystal of sea ice, culminates in a global current that influences climate from the depths of the Pacific to the shores of Europe. This is the connectivity of our planet, a connectivity of sublime subtlety and immense power. Let your breath slow to match this scale. Inhale, imagining that breath contains molecules of air that once circulated above the Weddell Sea. Exhale, releasing tension, as the deep ocean releases its ancient water back to the surface over millennia. Their rhythm here far slower than our own, a rhythm that has pulsed through ice ages and interglacials. For tonight, let your consciousness ride that slow, deep rhythm. But as the 20th century drew to a close, the silent river was no longer a mystery to be solved, but a vital sign to be monitored. A new anxiety began to thread through the scientific community. What if this ancient, steady pulse was faltering? The theoretical framework was in place. We knew the Antarctic bottom water was born of cold and salt. A warming world, it stood to reason, could disrupt that birth. But theory needed evidence, and evidence in the remote, storm-racked Southern Ocean was fiendishly hard to get. The quest entered a new technological phase. The heroic, ship-based campaigns continued, but they were now joined by silent, persistent observers. The first were the moored instruments. Imagine a vertical string anchored to the seafloor in the abyssal plain off Antarctica. Attached to it at different depths are sensors that record temperature, salinity, and current velocity, hour after hour, day after day, for years. These sentinels stood guard in the darkness, capturing the subtle variations in the deep flow that a ship's brief visit could never see. Deploying and retrieving them was a monumental task, a battle against ice, storms, and the sheer depth. But the data they sent back, via acoustic modems, or when finally recovered, was gold. It showed that the formation of bottom water wasn't constant. It pulsed. It varied with the fierce Antarctic winds and the year-to-year extent of sea ice. Then came the floats, the successors to Swallow's pioneering device. The Argo program, launched in the early 2000s, envisioned a global army of robotic profilers, over 3,000 of them, drifting with the deep currents. Every 10 days, an Argo float would pump oil into an external bladder, rise slowly from its parking depth of 2,000 meters to the surface, measuring temperature and salinity the entire way. At the surface, it would transmit its data to a satellite before sinking back to its depth to drift for another 10 days. These were the ultimate tools for mapping the ocean's interior in 4 dimensions. In the Southern Ocean, they began to capture the complex dance of water masses, revealing how pulses of dense water slid down the continental slope like underwater avalanches. But perhaps the most revealing perspective came from above. Satellites, equipped with radar altimeters, could measure the height of the sea surface with astonishing precision. Why does this matter for deep water? Because the ocean is not flat. Its surface is shaped by the hills and valleys of water density beneath it. Dense, sinking water creates a slight depression in the sea surface. By watching these surface depressions over time, satellites could indirectly infer changes in the deep formation processes around Antarctica. It was like diagnosing the health of a heart by watching the subtle movements of the chest. And the diagnosis, from the late 1990s onward, began to show signs of potential change. Several key studies, piecing together ship data, moorings, and models, suggested a startling possibility. The volume of Antarctic bottom water might be shrinking. The most dramatic evidence came from the Australian Antarctic Division. Repeat measurements in the deep basin south of Australia showed that the bottom water had become significantly warmer and less salty, and therefore less dense, over just a few decades. The signature of the pure, cold, dense source water was being diluted. It was as if the river's head spring was weakening. The suspected culprit? Freshening. Increased rainfall over the Southern Ocean, and more critically, increased meltwater from Antarctica's ice sheets and ice shelves. This meltwater is fresh. When it pours into the coastal seas, it forms a buoyant cap on the surface. This cap acts like a lid. It prevents the surface water from becoming dense enough to sink, even when it gets very cold. It stifles the process of brine rejection. The engine of the silent river was being gummed up. This wasn't just about the bottom water itself. The entire global conveyor belt is driven by the sinking of dense water at the poles. If the Antarctic pump weakens, the whole circulation could slow down. A slower conveyor belt transports less heat from the tropics toward the poles. The implications are counterintuitive and profound. A weakening of this system could lead to less heat reaching some regions, like parts of Western Europe, potentially altering weather patterns and even leading to regional cooling amidst global warming. It could also reduce the upwelling of nutrients that support marine life and affect how much carbon dioxide and heat the deep ocean can absorb from the atmosphere. The silent river, it turns out, is not just a fascinating feature of our planet. It is a key component of Earth's climate stability, and we are now conducting an unprecedented experiment upon it. Yet, amidst this modern urgency, there is still room for the awe that the early explorers felt. The science has become complex, filled with computer models, uncertainty ranges, and acronyms like CMIP and IPCC. But at its core, the story remains elemental: ice, water, salt, and cold. It is a story that connects the fate of the massive Thwaites Glacier, the so-called Doomsday Glacier, to deep ocean currents that will eventually brush against the Mariana Trench. It connects the decisions made in human cities to the slow breath of the abyss. For now, let us step back from the edge of contemporary anxiety and return to the sheer scale and majesty of the process. Picture the Antarctic coastline in winter. It is a place of almost unimaginable harshness. The sun is absent or low on the horizon. Temperatures plummet to -50 degrees Celsius or lower. The sea freezes outward from the land, the new ice groaning and cracking as it expands. In the Polynus, areas of open water kept clear by ferocious katabatic winds roaring down from the ice sheet, the heat loss is most intense. Here, the ocean gives up its warmth to the frigid air with shocking speed. The surface water chills to its freezing point. Ice crystals form, releasing their salt. The water beneath becomes a cold, heavy brine. This brine sinks, not in a single, visible stream, but in countless, diffuse plumes. Imagine millions of tiny, sinking fingers of the coldest, saltiest water on Earth, converging into a collective flow that slides along the seafloor. It moves with the patience of geology. It will take centuries to reach the equator. Along its journey, it will mix. It will warm infinitesimally. It will carry the chemical signature of its polar origin to every ocean basin. This is the rhythm we are part of, whether we know it or not. Our climate, our weather, the very fertility of the oceans are tied to this slow, polar heartbeat. As you listen, let your own heartbeat slow to meet this deeper, older rhythm. Feel the connection between the air in your lungs and the deep, cold water flowing half a world away. They are part of the same system, a system of glorious complexity and fragile balance. We stand now at a point in the story where our observation turns to projection, where understanding breeds concern. But the foundation of that understanding is the decades of painstaking work, the courage of those who sailed into the ice, the ingenuity of those who built the instruments, and the patience of those who pieced the puzzle together. Let that patience fill you now. The story of the silent river is not one of instant gratification. It is a story of gradual revelation, of clues gathered over a century, of a truth that emerges only when we learn to see on the scale of the ocean itself. As we conclude this first chapter in the story of the silent river, let us not dwell on the fear of its change, but on the profound wonder of its existence. For millennia, this process has unfolded in darkness, unseen and uncelebrated by the world above. It is a testament to the quiet, persistent forces that shape our planet far from the glare of human attention. Close your eyes and imagine the journey of a single molecule of water. It begins as part of a snowflake, falling gently onto the East Antarctic ice sheet. Over thousands of years, it is compressed into ice, traveling slowly toward the coast. It calves into an iceberg, which drifts into the sun-dappled Southern Ocean. The iceberg melts, releasing the fresh water. But our molecule is drawn into the winter sea ice formation. As the ice crystallizes around it, salt is expelled. Our molecule, now part of a dense, cold brine, begins to sink. It joins the Antarctic bottom water. For centuries, it travels north along the seafloor, through canyons deeper than the Grand Canyon, over plains vaster than any desert. It is part of a current that moves with the speed of a growing fingernail. It feels the distant rumble of undersea earthquakes. It passes through clouds of bioluminescent life in the midnight zone. It carries within it dissolved gases from the atmosphere of 1,000 years ago. Eventually, after a journey of over 1,000 years and 10,000 miles, it begins its slow ascent, upwelling in the North Pacific. It reaches the sunlit surface once more, perhaps off the coast of Japan. Here it evaporates, joins the clouds, and the cycle begins again. This is the epic that unfolds beneath the waves. A single circuit of the great ocean conveyor can take 1,600 years. Our entire recorded history is but a blink in the lifetime of a parcel of Antarctic bottom water. This perspective, the perspective of deep time and planetary connection, is the true gift of this story. In our daily lives, we are caught in the rapid currents of minutes, hours, and days. We worry about tomorrow, next week, next year. But the silent river invites us to expand our sense of time. It reminds us that we are part of a system that operates on scales that humble human concerns. This is not to diminish our lives, but to frame them within a grandeur that can be deeply calming. The anxiety about the river's future stems from love, from the dawning realization that this ancient, stabilizing pulse is not immune to our actions. But the river also teaches resilience. It has persisted through ice ages and warm periods. It will change, as it always has, but it is a feature of a dynamic earth. Our task is not to panic, but to understand, to respect, and to mitigate our impact so that the changes remain within bounds that allow civilization and the natural world to thrive together. For you, right now, listening in the quiet of your own space, let this story be a bridge to a deeper peace. Feel the weight of your body, supported by the earth. that Earth is crisscrossed by hidden rivers of water and air, all interconnected. Your breath is part of the atmosphere that interacts with the ocean. The water in your body has cycled through oceans, clouds, and rain for eons. In a very real, physical sense, you contain molecules that have journeyed in the deep, silent currents. So, as you prepare for sleep, imagine yourself not as separate, but as integrated. Imagine your awareness softening and spreading out, like a dye gently mixing into the deep ocean. Let go of the tight boundaries of the self. Feel your thoughts slowing, becoming as gradual as the deep-sea current. Your worries are like surface waves, real, but temporary. Beneath them lies a deep, cold, enduring calm. Visualize the map of the world. See the white continent at the bottom. From its edges, visualize gentle arrows of deep blue flowing north, spreading into all the ocean basins. This is the planet breathing, a slow, deep inhalation of cold water at the poles, a slow exhalation of upwelling water elsewhere. Let your own breath synchronize with this imagined planetary breath. Inhale cool, blue stability. Exhale warmth and surface tension. The story of the Antarctic bottom water is ultimately a story of connection, of how the most remote place on Earth touches every ocean, and by extension, every continent and every life. It is a story of how cold begets movement, and movement begets life. It is a hidden rhythm in the heart of our world. We will continue the story in our next chapter, delving into the modern tools that monitor this river and the scientists who listen to its whispers. We will explore the ice shelves that are its guardians and the uncertain future it faces. But for tonight, let the knowledge of its existence be enough. Let the simple, awesome fact of this silent, global river be your lullaby. You are part of a world that is far more intricate, connected, and wondrous than the busy surface of life often allows us to see. The same forces that send a river of cold water across the abyss also govern the flow of your blood, the rhythm of your heart. You are not outside nature. You are of it, and within it there is a deep, abiding peace to be found in the oldest, slowest rhythms of all. Now let the words fade. Let the concepts dissolve. Hold only the feeling of vast, cool, dark blue, the feeling of slow, inevitable flow, the feeling of being cradled in a system of majestic, timeless scale. Allow yourself to drift on that current. There is no need to steer, no need to think. Just be carried into the dark, into the quiet, into the deep, restorative peace that lies beneath the surface of everything. Our story of the silent river left the realm of early theory and entered the age of measurement. We now journey to the mid-20th century, a time when oceanography transformed from a descriptive science into a quantitative, globe-spanning endeavor. This is the era when the Antarctic bottom water ceased to be a hypothetical contour on a map and became a documented, flowing entity. The key to this transformation was not a single genius, but an international legion of scientists, engineers, and sailors armed with new tools and a collective determination to listen to the sea. The stage for this act is the research vessel, a world of steel, diesel, and purpose. Imagine the R/V Atlantis, the flagship of the Woods Hole Oceanographic Institution in the 1950s. It is a converted yacht, but sturdy, built to withstand North Atlantic gales. Now, picture it sailing not in the Atlantic, but further south, into the grip of the Southern Ocean. The crew and scientists aboard are pioneers in a literal sense. They are heading into waters for which few charts exist, driven by questions that have no easy answers. The central tool of their trade is the hydrographic cast. This is a ballet of precision and brute force. A metal frame, called a rosette, is loaded with 12, 24, sometimes 36 Nansen bottles. Each bottle is a simple masterpiece, a brass cylinder with valves at both ends. The rosette is lowered over the side on a thick, braided steel wire. The wire pays out from a winch, its hum a constant background noise on the aft deck. Meter by meter, the rosette descends into the green-gray water, vanishing from sight. The scientists watch the tension on the wire, the counters showing depth. They are aiming for specific horizons, 1,000 meters, 2,000 meters, 3,000 meters, all the way to within meters of the seafloor, which itself might be 4 or 5 kilometers down. At each target depth, a brass messenger weight is sent sliding down the wire. Clunk! It triggers a mechanism on the rosette, snapping one bottle shut, capturing a water sample from that exact depth. Another messenger is sent for the next bottle, and the next. It is a slow, methodical process. A single cast to the bottom and back could take 4 to 6 hours. In the freezing wind and spray of the Southern Ocean, it is an exercise in endurance. But in each retrieved bottle lies a treasure. The water is analyzed immediately for temperature and salinity. Later, in shore-based labs, it will be analyzed for dissolved oxygen, nutrients, and trace elements. From these measurements, scientists can calculate the water's density, and density is the compass that points to the movement of the deep. On the Atlantis, and on her sister ships like the Aire Puerto Deseado from Argentina or the Soviet academic Kachetov, thousands of these casts were performed. Station by station, a grid of data points began to cover the ocean south of 60 degrees latitude. When plotted, the results were stunning. The coldest, densest water was consistently found in 2 great embayments, the Weddell Sea and the Ross Sea. Here, the profiles showed a thick layer of water near the freezing point, sitting right on the bottom. Its salinity was the highest in the region. This was the source. This was where the silent river was being born. But to confirm it was a river, that it was moving, required a different kind of measurement. Enter the current meter. Early models were mechanical marvels. Imagine an underwater windmill. Its propeller would turn in the current, and a gear mechanism would record the number of rotations on a smoked glass disc or a paper chart. Alongside it, a vane would record direction. This entire instrument would be anchored to the seafloor for days, weeks, or months, faithfully recording the subtle flows in the abyss. Retrieving it meant sending an acoustic command to release its anchor, hoping it would float to the surface to be recovered. The data from these early current meters was sparse but revolutionary. In the deep channels leading out of the Weddell Sea, they recorded a persistent, slow flow to the north. The speeds were glacial, often less than 5 centimeters per second, but the direction was consistent. The cold, dense water was on the move. It was flowing along the seafloor, guided by the contours of the underwater landscape, seeking the deepest passages to spread into the world ocean. Yet, even with bottles and current meters, a fundamental problem remained: synopticity. A ship could only be in one place at one time. The ocean was vast, and its processes were continuous. How could one capture a snapshot of the entire system? The answer was ambitious: the multi-ship International Survey. The crown jewel of this era was the International Geophysical Year, IGY, of 1957 to 58. This was a moment of rare global scientific cooperation, born in the Cold War, but transcending politics. Dozens of nations sent ships to the Southern Ocean as part of the IGY. For the first time, multiple vessels worked in concert, performing standardized measurements along coordinated lines. It was like taking an MRI scan of the ocean. The IGY dataset revealed, with unprecedented clarity, the three-dimensional structure of the Southern Ocean. It showed how the Antarctic bottom water, once formed, flowed north through narrow gaps in the mid-ocean ridges, like water finding its way through a partially blocked drain. One of the most important discoveries from this period was the role of the Antarctic Circumpolar Current, ACC. This is the greatest current on Earth, relentless, eastward-flowing river of water that circles Antarctica, unimpeded by any continent. The ACC acts as a barrier, but also a mixer. The cold, dense bottom water must interact with it. Scientists found that the bottom water doesn't simply slide underneath the ACC. Instead, it is entrained and mixed along its boundaries. This mixing modifies the bottom water's properties, even as it exports it away from the continent. The silent river was not flowing in isolation. It was part of a complex, dynamic chorus of currents. The work was brutal. Storms that could snap steel cables, ice that could crush a hull, the perpetual gray twilight of the high-latitude winter. But the scientists and crews persevered. They were driven by a pure, burning curiosity to understand a fundamental piece of their planet. They were mapping the unseen, listening for the heartbeat of the deep. And with each cast of the bottle, each recovery of a current meter, the silent river became more real. It was no longer just cold, dense water. It was a water mass with a distinct identity, a history written in its temperature, salinity, and chemistry. They could trace its spread by following its core, the layer where the temperature was coldest and the oxygen content was highest, because it had recently been at the surface. This core snaked north through the Atlantic, Indian, and Pacific basins, like a cold vein through the ocean's body. As you listen, imagine the dedication of those early oceanographers, the long hours on a heaving deck, the meticulous note-taking in damp logbooks, the thrill of seeing a plot come together, revealing a pattern hidden from all of human history until that moment. They were the first to see the shape of the silent river. Let their patient, relentless pursuit of knowledge be a model for your own mind tonight. Let go of the need for instant answers. Embrace the slow, cumulative process of understanding. Each piece of data, like each breath you take, is part of a larger rhythm. In the darkness of the Southern Ocean, they found light in data. In the silence of the abyss, they found a story of magnificent motion. The 1960s ushered in a new level of sophistication. The simple Nansen bottle was joined by electronic marvels, the conductivity temperature depth, CTD, profiler. This instrument, lowered on a cable, could send a continuous stream of data back to the ship in real time. No more waiting for bottles to be tripped. Now, scientists on deck could watch a screen as a line snaked across it, tracing the precise change in temperature and salinity with every meter of descent. It was like watching the ocean's vital signs in a live electrocardiogram. The CTD revealed layers and fine structures invisible to the discrete bottle samples. It showed the sharp boundaries between water masses, places where temperature and salinity changed dramatically over just a few meters. These fronts were the walls of the river. They showed how the newly formed Antarctic bottom water, dense and cold, slid underneath slightly older, slightly warmer deep water. The CTD made the silent river visible in high definition. But to truly understand a river, you must also understand its chemistry. Water is not just H2O. It is a rich soup of dissolved gases, nutrients, and isotopes. These chemicals are tracers. They tell the story of where the water has been and what has happened to it. The 1970s saw the rise of geochemical oceanography, and its premier project was GeoSex, the Geochemical Ocean Section Study. GeoSex was an audacious global survey. Two ships, the Nor and the Melville, spent years circumnavigating the globe, stopping at hundreds of stations. At each, they didn't just lower a CTD. They collected water samples for a breathtaking array of chemical analyses. They measured dissolved inorganic carbon, alkalinity, nutrients like nitrate and phosphate, and a suite of radioactive isotopes. Among these, two were particularly powerful for tracing the silent river. The first was radiocarbon, or carbon-14, produced naturally in the upper atmosphere. It dissolves into the surface ocean. Once water sinks and is isolated from the atmosphere, its radiocarbon content slowly decays away. By measuring how much radiocarbon was left in a sample of bottom water, scientists could estimate how long it had been since that water had seen the surface. The answer was profound. The Antarctic bottom water in the deep Pacific had a radiocarbon age of over 1,000 years. This was direct proof of its antiquity and its slow journey. The second key tracer was tritium, a radioactive isotope of hydrogen. Unlike radiocarbon, tritium was largely absent from the natural ocean before the mid-1950s. It was injected into the atmosphere in huge quantities by the above-ground testing of thermonuclear weapons. This bomb tritium fell as rain and into the surface ocean, creating a sharp, man-made spike in concentration. It became a perfect timestamp. If scientists found tritium in the deep ocean, it meant that water had been in contact with the surface after the bomb tests, that is, within the last few decades. The geosex results were clear. In the core of the newly formed Antarctic Bottom Water near the continent, tritium levels were significant. This proved the water was modern, sinking from the surface within recent years. As they followed the bottom water north, the tritium signal gradually diluted and faded. By the time it reached the equatorial Atlantic, the bomb tritium was barely detectable. The river was carrying the chemical signature of the modern age into the ancient deep, a poignant reminder of how human actions can imprint even the most remote systems. Geosex also solved another puzzle, the aging of the river. As the bottom water flowed north, its oxygen content decreased, and its nutrient content, like silicate, increased. This wasn't due to pollution. It was the signature of life and death in the deep. Organic matter, the remains of plankton that died at the surface, slowly rains down through the water column. As this marine snow decays, it consumes oxygen and releases nutrients. The longer a parcel of water has been isolated from the surface, the more marine snow has decayed within it, and the lower its oxygen and the higher its nutrients. Geosex maps showed these parameters changing systematically along the path of the bottom water, providing a chemical road map of its journey. This chemical detective work was complemented by a growing understanding of the physics that guided the river. Henry Stommel's abyssal recipes and theories of thermohaline circulation were being refined into complex numerical models. For the first time, scientists could simulate the ocean on computers. These early models were crude by today's standards, but they captured the essential physics. Dense water forms at the poles, sinks, spreads, and eventually upwells. They showed that the ocean's overturning circulation was not a simple loop, but a turbulent, three-dimensional maze, with the Antarctic bottom water playing the starring role in filling the deep basins. The models also highlighted the importance of topography. The silent river does not flow over a flat plain. The seafloor is a rugged landscape of mountain ranges, deep trenches, and vast plateaus. The bottom water is channeled through key gaps. The most important of these is the Vima Channel in the South Atlantic, a deep, narrow passage in the mid-Atlantic ridge that acts as a choke point. Most of the bottom water flowing north from the Weddell Sea must pass through this underwater gorge. Discovering and measuring the flow through such passages became a critical focus. It was like finding the mouth of a terrestrial river. By the end of the 1970s, the silent river had been thoroughly documented. Its source regions were identified, Its chemical properties were mapped. Its pathways were charted. Its role in the global conveyor belt was established. Oceanography had progressed from wondering if deep water moved to describing how, where, and how fast it moved. But with this comprehensive knowledge came a new set of, perhaps deeper, questions. The system was now seen as dynamic, not static. What caused variations in the formation rate? Did it change with the seasons? With the winds? With the erratic dance of sea ice? And the most haunting question of all, lurking in the background, is this system constant over longer timescales? Could it have been different in the past? And could it change in the future? To answer these questions, science would need to move beyond snapshots. It would need to install long-term listening posts on the seafloor and develop tools that could monitor the river continuously in all seasons for decades. The age of discovery was transitioning into the age of monitoring. The silent river was about to get a chorus of permanent, electronic voices. As we absorb the magnitude of this mid-century scientific campaign, let us again appreciate the scale. This was a collective human effort spanning nations and decades. It required ships, funding, international treaties, and the shared curiosity of thousands of individuals. They built the foundational knowledge upon which all modern climate science rests. They proved that the deepest, darkest parts of our planet are connected to the surface, to the ice, and to the atmosphere in a continuous, physical dialogue. Let that sense of human endeavor and connection soothe you. In a world often focused on division, this story is one of collaboration in pursuit of pure understanding. Let your mind rest on that collaborative spirit. Feel your own consciousness as part of a larger web of curiosity and care for our planet. The silent river connects continents. The story of its discovery connects human minds across generations. The transition from expeditionary science to sustained observation began in earnest in the 1980s and 1990s. The silent river would no longer be measured only when a ship could brave the stormy seas. It would be listened to year-round by permanent sentinels on the seafloor. This was the era of the moored array, a technological leap that turned the deep ocean into a laboratory that never closed. Imagine the complexity of deploying such an array. A research vessel steams to a critical location, perhaps the exit of the Vima Channel, or a deep basin on the flank of the Antarctic continent. The ship must hold position in heavy swells. Over the side goes a massive anchor, weighing several tons. Attached to it is a long, robust chain of wire and synthetic rope, stretching up towards the surface. Along this vertical line, at precisely chosen depths, instruments are attached. At the very bottom, just meters above the seafloor, sits an acoustic Doppler current profiler, ADCP. This device doesn't just measure the current at one point. It sends out pulses of sound that reflect off particles in the water, allowing it to profile the speed and direction of the current for hundreds of meters above the seafloor. It paints a vertical slice of the moving river, Higher up on the mooring line are clusters of sensors: temperature, salinity, pressure. Some are simple recorders, storing data internally. Others are more advanced, with acoustic modems that can talk to a passing underwater vehicle or even send compressed data packets to a surface buoy, which then relays them to a satellite. The top of the mooring line is kept afloat by a large array of glass spheres, encased in hard plastic, designed to withstand the immense pressure. The entire structure, from anchor to float, might be 3, 4, or 5 kilometers tall. It is a towering, invisible monument to human ingenuity, standing upright in the perpetual darkness. Deploying it is a tense, all-hands operation. Retrieving a year or two later is an act of faith. The ship sends an acoustic command to a release mechanism just above the anchor. Ping. If all goes well, the anchor is let go, and the entire mooring, now buoyant, rockets toward the surface. The crew scans the horizon, waiting for the bright orange float to pop up, often kilometers away from where it was deployed due to subsurface currents. When it appears, it is a moment of pure relief and triumph. The data from these moorings revolutionized the understanding of the Antarctic bottom water. For the first time, scientists could see how the flow changed not just from place to place, but from month to month, season to season. They discovered pulses, or flushes. The formation of dense water wasn't a steady trickle. It was episodic. During particularly cold, icy winters, huge volumes of brine would form and sink, creating a surge of bottom water that would propagate downslope like an underwater avalanche. These pulses could be detected as sudden increases in current speed and drops in temperature of the mooring sites hundreds of kilometers away. The moorings also revealed the profound influence of the wind. The fierce, katabatic winds that scream down from the Antarctic ice sheet don't just chill the surface. They push surface water away from the continent. This process, known as Ekman transport, actually draws deeper water up to the surface to replace it, a process called upwelling. But this upwelled water is not the old bottom water. It is slightly warmer. When this upwelled water is exposed to the frigid air and ice formation, it can become even denser than before, creating a supercharged version of bottom water. The wind, therefore, wasn't just a bystander. It was an active pump, enhancing the engine that drove the silent river. While moorings stood guard at key choke points, another technological revolution was taking place on a global scale: satellite altimetry. From the 1990s onward, satellites like Topex/Poseidon and its successors began measuring the height of the sea surface with centimeter accuracy. How does this relate to deep water? The ocean surface is not flat. It bulges and dips in response to what lies beneath. Dense, deep water has a different mass than lighter water. This difference in mass creates subtle variations in Earth's gravity field, which in turn creates slight depressions in the sea surface above dense water masses. By meticulously tracking these sea surface height anomalies over years, scientists could indirectly infer changes in the volume and distribution of the deep, dense Antarctic bottom water. It was a way of weighing the river from space. The picture that emerged from these combined technologies, ships, moorings, satellites, was of a system both robust and variable. The silent river was always flowing, but its strength pulsed with the rhythm of Antarctic seasons and the beat of larger climate cycles, like the southern annular mode and El Niño. During a strong positive phase of the southern annular mode, which often means stronger westerly winds around Antarctica, more upwelling occurred, potentially leading to more bottom water formation. The river had natural variability, a kind of long-term breathing pattern. This understanding of natural variability was crucial, for it provided the baseline against which human-induced change could be measured. As the 20th century ended and the 21st began, the tools were in place not just to describe the river, but to diagnose its health. The focus was shifting from how does it work to is it changing? And the early signs from the moored arrays and repeat hydrographic sections were disquieting. In several key regions, the bottom water appeared to be warming and freshening. The signal was small, hundredths of a degree per decade, but it was persistent and statistically significant across multiple independent data sets. The silent river, it seemed, was feeling the effects of a warming world. The question was no longer purely academic. It was now urgent. How would the engine of the global overturning circulation respond to the rapid changes underway in the Antarctic? The story of discovery was becoming a story of vulnerability, and a race to understand the consequences before they became irreversible. But before we step fully into that modern chapter of concern, let us pause once more to marvel at the achievement. From the wooden ships of the heroic age to the satellite constellations of the digital age, humanity had unraveled one of the planet's great secrets. We had learned to see in the dark, to measure the immeasurably slow, to decode the chemical language of ancient water. We had proven that the ends of the earth are connected to the heart of every ocean. This knowledge is a testament to our species' unique drive to understand our home. As you rest, let that thought be a source of quiet pride and profound humility. We are the creatures who looked at a vast, stormy, frozen ocean and asked, "What moves in the deep?" And we found the answer. We listened, and we heard the silent river. Now, let the sounds of this endeavor, the hum of a ship's engine, the whir of a winch, the ping of sonar, the silent digital stream of data from the abyss, blend together into a lullaby of human curiosity. It is a gentle, persistent sound, much like the river itself. As our second chapter closes, we stand at the threshold between a century of brilliant discovery and a future of profound uncertainty. The silent river, the Antarctic bottom water, has been mapped, measured, and understood in its fundamental mechanics. We have followed its journey from the freezing brine of coastal Polyneus to its slow creep across the global abyss. We have learned its language of temperature, salinity, and chemistry. We have built machines to listen to its pulse from the seafloor and from space. But knowledge does not necessarily bring comfort. In understanding how the system works, we have also understood how it might break. The very factors that give the river its strength, intense cold and the creation of salty brine, are now under threat from a warming climate. The ice shelves that stabilize the glaciers are melting from below by warmer ocean water. The sea ice that forms the dense brine is showing worrying signs of retreat and thinning in key regions. The atmosphere over the Southern Ocean is warming and holding more moisture, leading to increased precipitation and freshwater input. All of these changes point in one direction: freshening. And freshening is the enemy of the silent river's engine. Fresh water is light. It floats. A cap of fresh meltwater on the surface of the coastal ocean can act as a lid, preventing the surface waters from becoming dense enough to sink, no matter how cold they get. It could, in theory, choke off the formation of bottom water, or at least significantly reduce its volume and density. This is not just speculation. The data from the sustained observations of the 1990s and 2000s began to show this fingerprint. In the Ross Sea, a major production site, the salinity of the shelf waters declined. In the Weddell Sea, the signature of supercold, dense shelf water became harder to find. The bottom water flowing through the deep channels seemed warmer and fresher than it was a few decades prior. The river was changing. The question shifted from "is it changing?" to "how fast?" and "what happens next?" The scientific community responded with a new level of coordinated effort. Programs like Orchestra and SOCM deployed fleets of robotic biogeochemical Argo floats across the Southern Ocean. These advanced floats not only measure temperature and salinity, but also pH, oxygen, nitrate, and chlorophyll. They give a holistic view of how physics, chemistry, and biology are intertwined in the river's journey. They operate autonomously under the ice, in the dead of winter, sending back data from places ships could never go. At the same time, icebreaker campaigns targeted the most vulnerable and critical regions. Ships like the Nathaniel B. Palmer and the British RS James Clark Ross spent months parked next to crumbling ice shelves like Thwaites Glacier, lowering instruments through boreholes in the ice to measure the warm water attacking from below. They mapped the seafloor to understand the pathways this warm water took. The story was no longer just about the deep river flowing out. It was also about the warm water flowing in. The modern narrative of the silent river is thus a tale of two opposing forces: the ancient, stabilizing force of polar cooling and sinking, and the new, disruptive force of global warming and ice melt. They are locked in a struggle whose outcome will shape the climate of the coming centuries. This can feel like a heavy burden to hold at the end of a long, contemplative story. But let us, for tonight, return to the perspective that this entire scientific journey has gifted us, the perspective of deep time and planetary connection. The silent river has flowed for millions of years, It has persisted through periods when Earth was far warmer than today, and through ice ages far colder. It is a resilient feature of a dynamic planet. It will not simply vanish, but can change its strength, its temperature, its pathways. And because our modern civilization, our agriculture, our coastal cities, our very weather patterns, has evolved during a period of remarkable climate stability, underpinned by ocean currents like this one, even a shift in the river's strength can have profound consequences for us. This understanding is not a cause for despair, but for clarity and purpose. We are not powerless observers. The story of the river's discovery proves our capacity for ingenuity and global cooperation. The same qualities that unmasked the silent river are now needed to protect its function. We have moved from the age of discovery to the age of stewardship. For you in this moment, let this knowledge settle not as a weight, but as a grounding connection. You are alive in a unique moment, the moment when humanity became aware of this deep, ancient rhythm. You are part of the first generation to see the full picture, to understand both the grandeur of the system and its fragility. This awareness is a form of kinship with the planet that previous generations never could have known. So, as we prepare to leave this chapter and eventually move to the next, where we will delve into the ice shelves and the front line of change, let us do so with a sense of balance. Hold both truths, the awe for the majestic, slow-moving river, and the sober understanding of the pressures it faces. In that balance lies wisdom. Now let go of the details. Let go of the data points, the instrument names, the acronyms. Let the core feeling remain. Picture the river, not as a line on a map, but as a presence. A vast, cool, dark presence moving with infinite patience through the world's deepest places. It is the planet's memory of cold, stored in liquid form and set in motion. It is a flow that connects all oceans into one. Imagine your own awareness softening and expanding to match the scale. Your thoughts are like surface ripples. Let them calm. Beneath them is a deeper, quieter state of mind, a state as patient and persistent as the bottom water itself. In this state, there is no urgency, only being. No problem to solve in this instant, only a connection to observe and appreciate. Breathe into that deep, inner stillness. With each exhale, release any tension clinging to you from the day. With each inhale, draw in the cool, steady calm of the abyss. You are not separate from the cycles of water and planet. You are a conscious point within them. Your breath is part of the atmosphere that exchanges gases with the ocean. Your body is mostly water that has cycled through oceans, clouds, and rain for eons. You are, in the most literal sense, a brief, conscious eddy in the great, slow flow of the silent river's world. And in that realization, there is a profound and unshakable peace. Let the final sounds of this chapter, the layered tapestry of technology and ocean, slowly simplify. Let the electronic pings fade. Let the winch sounds dissolve. Let even the deep drone soften until it is just a vibration on the edge of hearing. You are being returned to silence, the same silence that cradles the river in its deepest stretches. In our previous chapters, we mapped the silent river from its Antarctic source. We followed its cold, dense water as it slid along the seafloor, traced its chemical signature across ocean basins, and listened to its pulse with moored instruments. But a critical question remained. How does this river fit into the larger whole? Is the Antarctic bottom water an isolated phenomenon, or is it part of a planet-spanning system? This chapter tells the story of the brilliant minds who saw the pattern, who connected the dots across the global ocean, and gave us one of the most powerful metaphors in earth science, the great ocean conveyor belt. Our story begins not on a ship, but in a quiet study. Imagine a wood-paneled office at the Woods Hole Oceanographic Institution in the early 1950s. The air smells of pipe tobacco and old paper. At his desk sits Henry Stommel, a young, fiercely intelligent oceanographer with a restless mind. Stommel was already famous for his groundbreaking work on the Gulf Stream, but his curiosity was pulling him away from the sunlit surface, down into the mysterious abyss. At the time, the prevailing view of the deep ocean was that it was largely stagnant. It was a vast, cold repository, where water sat for millennia, unmoving. Surface currents were wind-driven and well-studied, but the deep was a void. Stommel wasn't satisfied. He looked at the sparse data on deep temperatures and salinities. He saw the cold pools spreading from the poles. He began to wonder, what if the deep ocean wasn't a stagnant pool, but a slow global river? In 1958, Stommel published a short, revolutionary paper titled The Abyssal Circulation. In it, he laid out a simple but profound idea. He proposed that the deep ocean is filled by dense water sinking in small, concentrated regions at high latitudes, primarily in the North Atlantic and around Antarctica. This sinking, he argued, must be balanced by a slow, broad upwelling across the rest of the ocean. This created a global overturning circulation, a vertical loop. Cold water sinks at the poles, spreads through the deep, slowly rises elsewhere, and returns to the poles at the surface to complete the cycle. It was a vision of the ocean as a dynamic, breathing entity. But Stommel was a theorist. He needed a collaborator with a more practical, chemical-minded approach to find the evidence. That collaborator was Arnold Arnie Gordon, a young oceanographer just beginning his career. Gordon was fascinated by water masses, distinct bodies of water with unique temperature and salinity signatures. He saw them as the ocean's blood types. In the 1960s and 70s, Gordon began meticulously tracking the spread of Antarctic bottom water and its counterpart, North Atlantic deep water. He used the growing library of hydrographic data to show how these dense waters flowed along the seafloor, like cold, heavy undercurrents beneath the familiar surface flows. The picture was becoming clearer. There were two great engines of deep water formation, one in the north and one in the south. But how are they connected? Did the water that sank in the North Atlantic eventually mix with the water from Antarctica? Did they form one continuous loop? Enter the geochemists. Scientists like Wallace Wally, broker of Columbia University's Lamont Doherty Observatory, began to look at the ocean through the lens of chemical tracers. Broker was particularly interested in radiocarbon. He realized that the age of deep water, how long since it had been at the surface, held the key to mapping the conveyor. In the late 1970s and early 1980s, Broker and his colleagues compiled radiocarbon data from geoscics and other surveys. The map they produced was stunning. It showed that the youngest deep water was in the North Atlantic, where it had recently sunk. This water flowed south, becoming progressively older as it moved. The oldest deep water was found in the deep North Pacific. This was the end of the line. The pattern was unmistakable. Deep water was moving from the Atlantic, through the Indian Ocean, and into the Pacific, where it eventually upwelled. The surface return flow was completed by warm, shallow currents like the Gulf Stream and the Agulhas Current, which carried water back towards the North Atlantic. The loop was closed. Broker, a master of communication, needed a vivid metaphor to explain this complex, three-dimensional global loop to the wider world. In a seminal 1985 paper in Natural History magazine, he called it the Great Ocean Conveyor Belt. The metaphor was perfect. It evoked an image of a slow, continuous, planet-sized machine. Water sinks in the North Atlantic and around Antarctica, gets on the conveyor belt in the deep ocean, travels through the ocean basins over centuries, and eventually rises to the surface in the Indian and Pacific Oceans to return to the start. The surface currents were the visible, fast-moving return leg of the belt. The conveyor belt metaphor captured the public and scientific imagination. It elegantly explained how the ocean redistributes heat from the equator to the poles, regulating global climate. It showed how the deep ocean is not a dead zone, but a critical part of Earth's living machinery. And, perhaps most importantly, it highlighted the system's potential vulnerability. A conveyor belt can, in theory, slow down or even stop if its driving forces are disrupted. For a silent river, the Antarctic Bottom Water, the conveyor belt framework gave it global context. It was no longer just a curious feature of the Southern Ocean. It was one of the two main engines powering the entire planetary circulation. The cold, dense water sliding from Antarctica was half of the heart that kept the conveyor moving. As you absorb this leap in understanding, feel the intellectual excitement of that era. Picture Stommel scribbling equations, Gordon painstakingly plotting water masses on charts, Broker connecting chemical dots across a globe. They were seeing a pattern invisible to everyone before them. They were discovering the planet's central heating and cooling system. Let that feeling of discovery, of connecting hidden dots, inspire a sense of calm wonder in you tonight. Your own mind is capable of making connections, of seeing patterns beneath surface chaos. As you rest, let your thoughts drift and connect freely, without force, like water masses finding their own level in the global deep. The conveyor belt was a powerful metaphor, but metaphors need rigorous testing. The 1980s and 1990s became the era of proving the conveyor's existence and measuring its strength. This required moving beyond snapshots and into the realm of sustained, quantitative observation. The scientific community rallied around a monumental goal: to measure the meridional overturning circulation (MOC), the technical term for the conveyor's north-south flow, directly in the field. The most ambitious target was the engine room of the conveyor's northern limb, the North Atlantic. Here warm, salty surface water flows north from the tropics via the Gulf Stream and its extensions. As it reaches the subpolar seas near Greenland, Iceland, and Norway, it loses its heat to the cold atmosphere. It also becomes salter through evaporation. This combination of cooling and increased salinity makes the water extremely dense. It sinks, plunging 2 or 3 kilometers down to become North Atlantic deep water, NADW. This sinking is the primary downward push that helps drive the entire global conveyor. To measure this, an international consortium of scientists designed and deployed the first basin-wide mooring array across the entire Atlantic at a key latitude, 26.5 degrees north. This was the Rapid Mocha Array, a technological marvel. A line of moorings stretched from the coast of Florida to the coast of Africa, each instrumented to measure currents, temperature, and salinity from the surface to the seafloor. The idea was simple in concept but fiendishly complex in execution. By measuring the flow northward in the warm surface layer and the flow southward in the cold deep layer, you could calculate the net overturning transport, the strength of the conveyor's Atlantic limb. The array was deployed in 2004. For over a decade, it provided a continuous stream of data. The results were revelatory. They showed that the Atlantic meridional overturning circulation, (MOC), was not a steady, unchanging flow. It varied significantly, on timescales from weeks to years. It had a seasonal heartbeat, and it responded to changes in wind patterns. The array provided the first continuous, direct proof that the conveyor belt was real, dynamic, and measurable. Its average strength was about 17 million cubic meters of water per second, a flow equal to about 100 Amazon rivers. But what about the southern engine? Measuring the formation and export of Antarctic bottom water was an even greater challenge. The Southern Ocean is more vast, more stormy, and ice-covered for much of the year. A moored array spanning it was impossible. Instead, scientists relied on a combination of tools: repeated hydrographic sections along key longitudes, a growing fleet of Argo floats that could profile under the ice, and focused moorings in the narrow choke points where the bottom water escaped from the Antarctic continental margin. The data painted a compelling, if complex, picture. The southern engine was more distributed than the northern one. Instead of a primary sinking site like the North Atlantic, Antarctic bottom water formed along vast stretches of coastline. Wherever sea ice grew and brine was rejected. Its formation was more sensitive to local winds and sea ice conditions, and its contribution to the global conveyor, while massive, was harder to pin down to a single, neat number like the Amok 17 spheredrops. However, the geochemical tracers continued to tell a unifying story. When scientists followed the spread of a man-made chemical like chlorofluorocarbon CFC, they could see both engines at work. CFCs entered the atmosphere, and thus the surface ocean, starting in the mid-20th century. Maps of CFC concentration in the deep ocean showed clear plumes spreading from the North Atlantic and from Antarctica. These plumes followed the predicted pathways of the conveyor. They mixed in the deep South Atlantic, and their combined signal flowed east into the Indian and Pacific Oceans. It was visual proof that the two engines fed into a single, interconnected deep flow. The conveyor belt model also provided a new lens through which to view Earth's climate history. Sediment cores from the ocean floor contained fossilized shells of tiny plankton called foraminifera. The chemistry of these shells records the temperature and chemistry of the water they lived in. By studying these cores, paleoceanographers like Jean-Claude Duplessis and later Jerry McManus found startling evidence that the conveyor belt had changed dramatically in the past. During the last ice age, the formation of North Atlantic deep water appears to have been much weaker, or even switched off at times. Meanwhile, the Antarctic bottom water may have been relatively stronger. This shift in the conveyor's balance coincided with abrupt climate events recorded in Greenland ice cores, events where temperatures in the North Atlantic region swung by 10 degrees Celsius or more in just a few decades. The implication was profound. The conveyor belt is not just a passive feature of climate. It is an active player that can amplify and trigger rapid climate change. This paleo record turned the conveyor from a fascinating modern phenomenon into a key to understanding Earth's climate sensitivity. It showed that the system had different modes of operation, and it suggested that the transitions between these modes could be shockingly fast. Wally Broker popularized this idea with another powerful phrase, warning that global warming could potentially cause an abrupt change in the conveyor belt circulation. For the silent river of Antarctica, this historical context added a new layer of meaning. Its strength relative to the northern engine could dictate global climate patterns. A shift in its formation rate wasn't just a local Antarctic issue. It was a global climate event in making. As you listen, let the scale of this interconnected system fill your awareness. Picture the two great engines, one in the north, driven by heat loss, one in the south, driven by ice and brine. Picture the slow, global flow connecting them through every ocean basin. This is the planet's lifeblood, circulating heat, carbon, and nutrients. We have only become aware of its full scope within the last few decades. We are the first humans to hold this complete picture in our minds. Let that fact humble and quiet you. The anxieties of daily life are surface ripples. Beneath them flows this ancient, powerful rhythm that has shaped climates for millennia. Align your breath with that deeper rhythm. Inhale, drawing in the stability of a system that has endured ice ages. Exhale, releasing the surface noise. You are connected to this deep, slow pulse. It is part of the world that sustains you. The discovery of the conveyor belt and its paleoclimate significance did more than advance science. It changed our perception of the ocean's role in climate. The ocean was no longer seen as a passive thermal buffer, but as an active, dynamic driver with its own inertia and the potential for dramatic regime shifts. This understanding set the stage for the final, ongoing chapter of our story, monitoring the conveyor's health in real time, diagnosing its response to modern climate change, and grappling with the profound implications. The 21st century saw the deployment of even more sophisticated observing systems. In the Atlantic, the Rapid Array was joined by the OSNAP, overturning in the subpolar North Atlantic program. Array, a network of moorings further north, designed to catch the sinking process itself, to measure the water as it cooled, densified, and plunged into the abyss. In the Southern Ocean, programs like SOS, Southern Ocean Observing System, coordinated an international fleet of ships, floats, gliders, and satellites to monitor the Southern Engine with unprecedented resolution. The data from these systems began to reveal early warning signals. In the North Atlantic, the surface waters were freshening due to increased precipitation and meltwater from Greenland. Fresher water is less dense, making it harder to sink. Some studies suggested a weakening of the AMOC by about 15% since the mid-20th century, though the record was still short and the natural variability large. The trend, however, was in the direction climate models predicted for a warming world, a slowdown. In the Antarctic, the signals were more complex, but equally concerning. The warming of the deep ocean was accelerating the melt of ice shelves from below. This meltwater was a direct, fresh input to the coastal seas, where bottom water forms. In key regions like the Amundsen Sea, the signature of the supercold, salty shelf water needed to make the densest bottom water was becoming harder to find. The recipe for the silent river was being altered. Climate models, which now included sophisticated representations of ocean physics and ice sheets, projected a consistent future, a weakening of the global overturning circulation over the 21st century. The degree of weakening depended heavily on future emissions. In high-emission scenarios, some models showed the AMOC collapsing entirely by 2300, with the Antarctic Bottom Water formation also significantly reduced. The conveyor belt, which has shaped Earth's climate for thousands of years, was entering uncharted territory. This is where our story of the silent river converges with the most pressing question of our time. The Antarctic bottom water is not just an object of curiosity. It is a climate regulator of the first order. By driving the lower limb of the conveyor, it helps sequester heat and carbon dioxide in the deep ocean. A weaker conveyor means less heat is buried in the abyss, leaving more to warm the atmosphere and the surface ocean. It also means less carbon dioxide is drawn down, potentially accelerating atmospheric warming. It is a feedback loop with global consequences. But let us pause here, at the brink of this potential future. Let us not be carried away by fear, but grounded by the profound understanding we have gained. The story of the great ocean conveyor belt is, above all, a story of connection. It connects the Arctic to the Antarctic, the surface to the abyss, the past to the future, and physics to chemistry to biology. It connects human emissions in one hemisphere to ocean changes in another. It is the ultimate expression of Earth as an integrated system. For you, tonight, let this deep connectivity be a source of calm, not anxiety. In a world that often feels fragmented, the conveyor reminds us of fundamental unity. Every breath you take contains oxygen that was once dissolved in this global circulation. Every drop of water you drink has passed through it. You are not separate from this system. You are of it, and it sustains you. This knowledge invites a shift in consciousness, from seeing ourselves as apart from nature, to understanding ourselves as participants within a vast, ancient, and delicate web of processes. With that shift comes responsibility, but also a deep sense of belonging and peace. The same currents that fear might weaken are the currents that have cradled the development of life and human civilization. So, as we approach the conclusion of this chapter on the conveyor's discovery, let us hold both truths in balance: the scientific truth of its vulnerability and the existential truth of our connection to it. The appropriate response to this knowledge is not paralysis, but a calm, clear-eyed commitment to stewardship, born from a place of understanding and reverence. Now, let the complex data streams, the model projections, and the scientific debates soften in your mind. Return to the simple, powerful image: a belt, a loop, a circulation, a slow, endless exchange between the poles and the equator, between the light and the dark, between the past and the future. This is the rhythm of your planet. Let your awareness rest within that rhythm. We have journeyed from the first inklings of deep motion to the sophisticated map of a planet-spanning conveyor belt. We have seen how the silent river from Antarctica is not a solitary flow, but one essential pump in a global heart. This understanding is humanity's shared achievement, a testament to curiosity, collaboration, and perseverance across generations. As we close this chapter, let us integrate this knowledge not as a burden of worry, but as a foundation for profound, deep-time peace. The great ocean conveyor belt operates on a timescale that dwarfs human history. A single loop takes about 1,600 years. The water sinking today in the Weddell Sea will upwell in the North Pacific around the year 3600. The system's rhythms are measured in centuries and millennia. Our individual lives, our civilizations, even our species' entire history, are but brief moments within one cycle of this immense, slow-motion wheel. This perspective is inherently calming. It places our current anxieties, personal, societal, environmental, within a context so vast it can dissolve their sharp edges. The conveyor has persisted through epochs when continents were in different positions, through atmospheric compositions alien to us, through temperatures both hotter and colder than today. It is a feature of a dynamic, resilient, and ever-changing Earth. Our modern concerns, while urgent and real for us, are part of a much longer, more patient story. This is not to suggest inaction. Quite the opposite. Understanding our place within deep time can clarify our purpose. We are the first generation with the knowledge to see how our actions affect planetary scale systems like the conveyor. This gives us a unique responsibility to become conscious stewards, to align our short-term actions with the long-term health of these stabilizing rhythms. But this stewardship can arise from a place of connection and awe, rather than fear and panic. So, how do we carry this awareness into rest? We practice aligning our personal rhythm with the planetary rhythm we've learned about. Begin with your breath. Let it slow. Inhale deeply, imagining you are drawing in the cool, stable certainty of the deep abyss, the realm of the silent river and the conveyor's lower limb. Hold that breath for a moment, feeling the stillness and weight of ancient water. Exhale slowly, releasing not just air, but any surface tension, any frantic mental energy, sending it back into the circulating system to be transformed. Now, bring your attention to your body. Feel its weight supported by the earth. That earth is spinning through space, its ocean slowly turning over, its heat being redistributed by the very conveyor we've explored. You are physically connected to this process. The calcium in your bones once cycled through the ocean. The water in your cells has been part of clouds, rain, rivers, and possibly even the deep polar currents. You are not on the planet. You are of the planet. Your body is a temporary collection of atoms that are, and always have been, part of this grand circulation. With this feeling of physical integration, allow your mind to expand. Visualize the globe from space. See the white cap of Antarctica. From its edges, visualize a gentle, deep blue current beginning to flow north along the seafloor. See its counterpart in the North Atlantic, another sinking plume. See these deep flows connecting, spreading through all ocean basins. Then see the surface return flows, the warm, visible currents like the Gulf Stream, completing the loop. See it as one continuous, graceful movement, a planetary dance of energy and matter. Now imagine your consciousness gently dissolving into that blue flow. Let go of the sense of a separate you located in a room. Instead, feel yourself as awareness distributed within the flow, cool, patient, and moving with purpose but without hurry. There's no struggle here, only the inevitable, slow fulfillment of physical laws. Gravity, density, temperature, salinity. These simple forces create a ballet of sublime complexity. Your own thoughts can become like this, natural forces interacting, creating temporary patterns before dissolving back into the flow. This is the deep peace offered by the story of the silent river and the conveyor belt. It is the peace of knowing you belong to something ancient, vast, and beautifully ordered. It is the peace that comes from releasing the illusion of separation and control, and instead resting in the certainty of your interconnected existence. The challenges facing the conveyor are real. The scientific work to monitor and understand them is critical. Our societal choices to reduce the pressures on the system are essential. But tonight, let your role be that of the observer, the appreciator, the one who rests within the system to draw strength from it. Tomorrow, that strength can fuel action, but for now, let it fuel deep, restorative sleep. Let the sounds that have carried us through this chapter, the deep pulse, the planetary breath, begin their final, gentle descent. They have been the auditory representation of the conveyor's rhythm. Now, as you sink towards sleep, let them guide you down, just as dense water sinks into the abyss. You are cradled in the deep, turning world. The river flows. The conveyor turns. You are part of it all. Let go and be carried. Good night.